Hi, so my name is Aaron and I'm going to be discussing question 2 on tutorial sheet 4, which is discuss the following terms in relation to controller implementation. A. Proportional band. B. Linearity. C. Disturbance. D. Integral windup. E. Proportional kick. And F. Derivative kick. So, proportional band. Proportional band is the amount of change in error that will cause an output to go from full on to full off. The amount of change in error is calculated was the percentage of the full scale error. This can be also defined as PB is equal to 100 over KP, which is the gain. The figure below shows examples of the proportional band. So if the PB is a span of 25%, which is equal to 25% of the span. Example, the process controller is 600 units, so 25% is 150 units wide. Below the 150 units wide window, the process is full on. Above the window, the process is full off. Inside the 150 units wide window, the process is on or off at sliding analog percent. So as we can see from the bottom picture of the above, we have a 25% band, so it's off below and it's on above. So the linearity is the property of a mathematical relationship function that can be graphically represented in a straight line. Linearity is closely related to proportionality. So if we look at the graph below, we have a weighing scales. So we have the actual weight is on the left hand side and the displayed weight is on the bottom. So as the person stands on the scales, we have a perfect relationship between the actual weight and the displayed weight. If this was a non-linear line, we wouldn't get a straight line. We would have curves in it. So disturbance. Disturbance is a state at which normal mental or physical functioning is disrupted. A disturbance signal represents unwanted frequencies which affects the control system's output and results in an increase in system error. So if we look at the picture below, we can see the airflow of the aerodynamics of a Formula One car. The idea behind the Formula One car is that it's able to cut through the air and have the least amount of air resistance. So as we can see on the tires, we have the most resistance, which are the red areas, and all the lighter colors show where the resistance is minimal. So this allows the Formula One car to have the least amount of disturbance to produce more fuel efficiency and to allow the car to go faster. Integral windup, also known as integrator windup or reset windup, refers to the situation in a PID feedback controller where a large change in set point occurs and the integral term accumulates a significant error due to the rise and overshooting continues to increase as this accumulated error is unwound. So as we see, we have our set point and the integral performs doesn't go straight up where it creates an area under the graph for a set point and then produces a small overshoot which is based on the sum of the errors. So SP is equal to minus PV. So proportional kick. Controller gain can be made negative or positive. So direct acting on K is less than 0 or which is shown on B on the graph, or reverse acting, which is K is greater than 0 along the y-t axis. So as K is greater than 0, we have an increase in we have a as the input increases, the output increases, and as k is less than 0, it shows the system going back to 0. So, and our derivative kick occurs because the value of error changes suddenly whenever a set point is adjusted. The derivative of a sudden jump in error causes the derivative of error to be instantaneously large and causes the controller output saturate for one cycle at either upper or lower bounds. So as we can see from the graph, the natural line goes just gradually builds up, whereas our output sees a spike um, at the two changes in our set point. This causes a derivative spike.